Hey, welcome back. Today we're going to be talking about how to solve for angular acceleration with rolling objects, specifically rolling without slipping. This is primarily for AP Physics C mechanics students and AP Physics 1 students, but these types of problems can be done by any good, solid, maybe an honors physics level class. Like, you don't need any calculus to be able to do this. It's a good set of skills to review a rotation unit, so that's what we're going to be doing today. And so let's go ahead and get to it. This problem says a thin hoop with a radius r is at rest at the top of an inclined plane. The hoop has a mass of m, the hoop is released from rest, and it rolls without slipping down the inclined plane. Determine an expression, so that's an equation, right, for the angular acceleration and the linear acceleration of the thin hoop. So that's what we're going to do. Let's go ahead and get to it. Okay, and so one of the first things we need to do here is to decide on the forces. So what are some forces that are affecting this? Well, the first thing to talk about is gravity. Gravity is going to be pulling straight down even though the hoop doesn't actually exist right in the center. In other words, that's just the center of mass for the hoop. So we still apply it at the center though. And it's really crucial to start thinking about where forces are applied when we're working with rigid shapes that have torque possibilities. So that's going to be applied right at the center of mass. How about the normal force? What do you think we could do with that? Well, it is still perpendicular to the surface, but really important here, I'm going to draw this differently than you might expect, because previously in previous units where we haven't worried about torque, we've just drawn a dot for the object and then drawn the normal force as being perpendicular. Here it's of course perpendicular as well, but it's really crucial that we understand we need to draw that from the point of contact that the hoop has with the ground. And the last force we have to deal with is going to be the frictional force, and that will also apply right at the point of contact with the ramp. So I'll label this as generalized friction. Now immediately what we can do is look at our forces and see if there's anything that's not in the x or the y or the z axis, and that would be the force due to gravity, and start thinking to yourself, alright, I'm going to draw this as the hypotenuse to a right triangle that's off to the side, so this we'll just call FG and break that down immediately into mg. This we'll call FGX, and that is going to be equal to mg sine of theta. Notice this theta is over here, and the last one is going to be FGY is going to be equal to mg cosine of theta. So that's going to be this leg of the triangle right here. Very good. So again, do that off to the side, not on your free body diagram. If you're practicing for FRQs, you should be practicing this as well, because if you draw components on a free body diagram, you will miss points on the test itself. Okay, and then let's proceed with our normal strategies, and I will show you multiple ways to be able to solve these problems. So the first strategy I would expect my students to use, and I want to encourage everyone to use, is what I call the sum of the forces strategy. So the sum of the forces strategy, you literally sum up the forces in that axis. So let's think about what we have here. We've got an FGX, plus we have a negative force due to friction here, and that's it. And the second line for the sum of the forces strategy is just m times acceleration in that axis, and that's Newton's second law. And because these things are the same, we can set them equal to each other. It's also really important at this point to ask ourselves, is this thing, this acceleration here, is it something or nothing? What do you think? Well, in this case it's something, so we cannot just get rid of it like we can sometimes. So we're going to say FGX minus the force due to friction is going to be equal to MAX. And we know something about this FGX. We just solved for it. We said that is mg sine of theta minus the force due to friction is equal to MAX. I'm going to label this as 1 because the College Board, in giving this example, does something special with this that I would do differently, but it actually just depends on what the question is that you're being asked. And so I'm going to show you multiple ways of thinking through this in very logical fashion. Let's move on to the y-axis and do the same sum of the forces strategy. So the sum of the forces in the y here is equal to Fn plus a negative Fgy. And the sum of the forces in the y we say is equal to mass times acceleration in y. Again, ask ourselves, is this acceleration in y something or nothing here? What do you think? Well, in this case, it's going to be nothing, and that's because the object is not like magically going up in the atmosphere or down into the ramp, not even moving in the y-axis, so we can set these things equal to each other and know that the sum is equal to 0. So we say Fn minus Fgy is equal to 0. So therefore Fn is equal to Fgy. That's true in terms of magnitude, not in terms of direction. And we can say Fn is equal to mg cosine of theta. So that's important. We're going to put that in a box for now, and we'll box this up as well. And then the next strategy that I would normally expect my students to work with is you work in the x, you work in the y, and you bring them together. With the friction equation, that's what's special about the friction equation, is it draws on the x-axis and the y-axis. So I'm going to work with that here. And again, we're using a generalized friction equation. You can do this for most AP problems. If it was a specific problem, it would be static, but because we just can assume that we have maximum friction force involved, then that less than or equal to symbol that's in the static friction equation just becomes an equal sign. So we're going to simplify it, just write it this way. All right, we do know something about the force due to friction. We say the force due to friction now is equal to mu mg cosine theta, because that's what we would solve for previously. We could, at this point, plug it in, and so I could say sort of a dot, 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 and move it over here and see what we have. We could say mg sine of theta minus mu mg cosine of theta is equal to ma, and that axis. And before we move on, what can we do to simplify the equation? Well, we can get rid of the m's, right? So if we get rid of the m's, then we have g sine of theta minus mu g cos of theta is equal to acceleration of the x. And if we want to, we could factor out the g and say g sine theta minus mu cosine theta is equal to acceleration of the x. In other words, I'll show that right now. Okay, so you can write this in a couple different ways. Either way is going to be fine. These are some of the strategies I would normally approach a problem with and expect my students to approach a problem with. We can even build on this, and we should build on this and work with torque. That's what's newer in this unit. We're working with torque as well, and we're going to use the same strategy in a rotational sense. So we say the sum of the torques. Now, this is what I'm about to say here is actually really important. I want you to consider which of these three forces, how many of these three forces, or which ones will apply torque. What do you think? Well, the answer is only one will apply a torque, and that's going to be the force due to friction. So let me talk you through it. The normal force does not apply a torque because its force is in the same plane as the r vector itself. So there's no perpendicular component to the r vector to apply a torque at all. And the force due to gravity applies no torque because it's applying right at the axis of rotation. That would be like saying, how much torque would you apply on a door if you pushed right on the hinge of the door? And the answer would be nothing. Like, there would be no torque. And so the only force that's applying a torque here is going to be the force due to friction. So we could say this is the torque from friction. And the second line for the sum of the torque strategy is just the rotational version of ma, which is I times alpha. We can set these equal to each other, and just in the interest of saving some space, I'm going to put these up here and say torque from friction is going to be equal to I times alpha. And so what is that? Well, that would be the radius. They call it a capital R here, so I'm going to be careful to use what they use, times the force due to friction is equal to I times alpha here. And I'm going to label right around here, somewhere around here. The College Board does something interesting and creative. I could take my version of it though and show you what I'm talking about here. I'll also apply it down here. So, I do want to mention at this point, for the I value, the moment of inertia, we need to sub in the equation for moment of inertia for a hoop, which is mr squared. So that's what I've done here. At this point, I would sub in my previous work for the force due to friction, which is up there. And because that's the force due to friction here, so I'll show you what I would do, and then I will work with number 2 and show you what the College Board might do slightly differently. And you're just going to get both correct answers, but written with different variables. So I'm going to explain in a second. So let's go ahead and sub in what our force due to friction is. Okay, and so this is what we have. Notice sometimes you can get like a lowercase m and a capital M. There's some historic reason, I'm not quite sure why, that the moment of inertia equations are written with big M for mass and big R for radius, but they mean the same thing, so don't get confused or thrown off by that. So like this little m can cancel out the big M on the right side. And then notice we also have this R, cancels out one of these R's over here. So what are we left with? We're left with this. So therefore we can say alpha is equal to divided by R. Okay, so that is one way of thinking about this. You can also apply that differently. Remember this small but mighty equation I talked about right here, and its acceleration corollary is this over here. So we can take that and just say, well, what if we have a over r that would be equal to alpha? So you could also sub this in for alpha and see what pops out as well. So that's one way of solving this and working with this. But I do want you to notice that for this version over here, I'll put a green check mark. Notice that the answer that we're getting is using mu here. And I think the College Board goes a different route with explaining this problem because sometimes you are restricted in the variables that you can use for an answer. And so it's useful to think in different ways and like, how do we solve problems without mu, for instance? Maybe that's something that you're not allowed to do. Or just to think about this differently. Let's think about this differently and think about what the College Board would do differently here. Okay, so I'm going to write this in white and drag over the equations that we have to work with. If you work with this equation here, notice that one of these r's can get canceled out in both cases. So you can solve for the force due to friction here, and that is just going to be mr alpha right here. So you can say, well, let's go ahead and take this and sub it in. I'll draw like a dotted line to kind of get the idea. Sub it in over here and see what happens. And so if we were to do the problem this way, what do you notice that we can do immediately to simplify the equation? Okay, well, we can get rid of the m's, right? And then we can also, remember we talked about how we have this equation right here. And this acceleration can be treated as a tangential acceleration or as the center of mass sort of acceleration, the linear acceleration. So let's sub that in here and see what happens. And notice that we've got two terms that are r times alpha, so let's bring them together. And if that's the case, then we can still isolate for alpha, and if we do that, then we end up with this. Okay, and so notice that we have now solved for this. I mean, there's another step we could do if we wanted to. We could take this equation right here and say, sub this in for a and just see what happens as well. And notice that we've got r on both sides, so we can cancel that, and we can end up with this, g sine theta over 2. Okay, so let's compare what they have done with what I might have done just out of habit based on what else we've done in the past and strategies I've gone over in the past. Notice that these are just similar equations here that are written with different terms. So again, notice that we have this mu in the first version. Over here, there's no mu in the acceleration version that we've solved for differently. So you should be able to approach things in both ways depending on what you're needing to do and solve for. And sometimes you're just given limitations by the College Board. Oh, one more really important thing I want to bring up, and that is, let's practice our right-hand rule for this situation. So think about what the right-hand rule is going to be for our acceleration here. So the only thing that's applying a torque here is the force due to friction. So I want you to practice the right-hand rule right now using that force due to friction and the torque that's applied to come up with the acceleration, because net torque causes acceleration. So it's going to be the same direction. The direction of the net torque vector, which is the torque due to friction, is going to be in the same direction as the acceleration vector. So what would that direction be? Well, if you think about the right-hand rule, what you should do right now is have your right hand pointing downwards, down the negative y plane, and then curl your fingers towards the FF direction. And notice that if you do that, your thumb is pointing into the screen. So if it's pointing into the screen, I'm going to go ahead and circle this. The vector in this case that I've drawn right here with this setup as negative z is going like into the page, positive z would be coming out of the page towards us. Then the vector of the net torque and the angular acceleration is going to be in the negative z direction. Okay, I do want to say finally that I've gone over screencasts for an entire year of physics as well as most of the concepts for AP Physics E mechanics. If you have any questions or comments down below, please let me know, and I hope you all have a great day. Take care.